Hi everyone, I am Mingzi Chen, a student of CS6263, Intro to Cyber-Physical Systems Security. And today, I will be presenting a paper named OK Siri or Hey Google, evaluating Voiceprint distinctiveness via content-based PROLE score. Here is our agenda today. First, we're going to talk about the overview and motivation of this paper. Then we will talk about the problem statement and the challenges and methodology. After that, we will talk about the PROLE score and solution. And finally, we will talk about the findings and conclusion. By the end of the presentation, we would help the audience understand what kind of speech content can improve the security of Voiceprint. Voiceprint is a measurable characteristic of human voices. It is a popular biometric verification method. It is widely used to unlock phones, authorize payments, and wake up smart speakers. Therefore, the security of Voiceprint is important, and it affects various industries. The distinctiveness of Voiceprint is essential to the security of Voiceprint. Distinctiveness means that any two people do not have the same Voiceprint. Given two users, one user will not be able to be classified as the other. An example is that if the distinctiveness of the Voiceprint is low, Bob can impersonate Alice to control the smart speaker. Here is an example about the extracted Voiceprint depending on the speech content. What types of speech content can provide secure Voiceprints? Alice's Voiceprint of OK Google is different from that of Hey Siri and provides different levels of Voiceprint security. A Voiceprint is essentially a spectrographically produced mathematical representation of human voices, and its distinctiveness has four contributors. First, intrinsic physiological features of a speaker. For example, the vocal tract shape. Second, speech contents. For example, words with various phonetic alphabets. Third, ASV models that are used to derive and compare Voiceprints. And fourth, the environment and equipment factors. For example, environmental noises, acoustic channel responses, or variance caused by device properties, as shown in the figure. One of the problem statements is, what types of speech content can provide secure Voiceprints? Also, by studying 2,457 speakers and 14,600,000 test samples, we provide the answers to the following three questions. First, what are the influential factors that determine the distinctiveness of Voiceprints? Second, how to quantify the distinctiveness of Voiceprints for given words. For example, wake-up words in commercial voice assistants. And the third question, how to construct wake-up words whose Voiceprints have high distinctiveness levels. Now, we would like to introduce the challenges and methodology of providing secure Voiceprints. We construct a Voiceprint security scoring metric. For example, the input, which is the speech content, is OK Siri. The scoring function, S equals FC, will calculate the security score and output a security score and a security level. If you input Hey Google, the scoring function will give you the corresponding score. With the scoring function, we can design more secure speech contents and generate words and phrases with a more secure voice print. High security score is related to high distinctiveness and low false recognition rate. False recognition rate includes false acceptance rate and false rejection rate. A typical scenario to use our PROLE score is for commercial wake-up words. Smart speaker companies find good wake-up words, and most commercial wake-up words consist of one or two words with a prefix word, such as OK Google, Hey Siri, Hey Cortana, and 你好, 小易. So, do these wake-up words provide enough distinctiveness in Voiceprint? Our metric, Voiceprint Security Scoring Matrix, helps us answer three important questions. First, whether the wake-up words are secure. And second, why are they secure or insecure? And third, how to design secure words. So, how to construct the scoring metric? First, we investigate the automatic speaker verification system, which refers to the workflow presented on the slide. We can use this workflow to find the security of Voiceprint, which is affected by four modules, including speaker, speech content, environment, and the automatic speaker verification model. So, how to get a PROLE score when the user provides the speech content only, but not the rest of the modules? To construct a universal score, there are two challenges. First, the score should adapt to most speakers, environment, and ASV models. Second, the capability of handling a wide variety of speech content. The solution to the first challenge is to conduct a large-scale analysis. With 2,457 speakers of various genders, speech speeds, channel noises, etc., and over 1,000 hours utterances or samples, with three typical models, including I-vector, X-vector, and U-level, with two speech datasets, the VCTK and Libri speech datasets. These combinations represent most cases. Therefore, the score can adapt to most speakers, environment, and ASV models. The second challenge is for the score to adapt to a wide variety of speech content. The solution is to use comprehensive speech content, which is to compose test audio samples of arbitrary speech content by concatenating the basic unit phones naturally. We use the 1,000-hour sample and segment the sample into phone clips and reassemble them to test audio samples, which gives us more than 40 million audio samples. Our measurement methodology comes in three key steps. First, we analyze what phonetic factors we can derive from the speech content. Then, to test the relationship between the content and the distinctiveness, we construct a dataset with contents that are general enough. Third, we perform a model fitting on the measurement results of this dataset to get the PROLE score. Now, we will introduce the components of the scoring metric, PROLE score. PROLE score is our solution to the Voiceprint security metric. We would like to model the speech content with the basic unit of language, phone. A sentence can be viewed as a sequence of phones. We represent the speech content with some features. We define 4 phonetic factors: richness, length, element, and order. Richness means the number of phone types. In Hey Google, there are 7 phone types. Length means the number of phones. In Hey Google, there are 8 phones. Element means the specific type of phones, which are H, A, G, U, E, and L. Order means the sequential relationship among phones. For example, H is in front of A. Then we map the phonetic factors to the security score. The scoring function has 7 variables, which includes 4 phonetic factors and 3 implicit variables, which are model, speaker, and environment. The output of the function is called the PROLE score. Now, based on the false recognition rate, we parameterize the PROLE score. The parameterization comes in 2 parts. 1. We would like to find out about the impact of a single factor. And 2. We would like to rank the influence of the 4 factors. Let's take a look at the statistical results of false acceptance rate and false rejection rate on the audio samples. We see that as the richness increases, the security increases as well. And when the richness is higher than 5, its impact becomes negligible. We can fit the impact of richness as an exponential function. Here is an example that shows the difference in richness. Google versus Hey Google. Google has a richness of 4, and Hey Google has a richness of 7. We see that Hey increases the richness by 3, which improves the security. Our finding is that the richness of the speech content should be at least 5. The statistical result for length is similar to that of richness. When the length is greater than 13, its impact is negligible. Here is an example. 小度 has a length of 7, and 小度 has a length of 14, which has higher security. Our finding is that the length of the speech content should be at least 13. For element, the graph shows the sum of false acceptance rate and false rejection rate on a diverse pool of phones, such as I, O, D, in 3 models. A lower bar on the graph means higher security. We find that there are some magic phones with low false recognition rates and generate better and more distinct voice prints. For example, I is better than O in 3 typical models. An example is a comparison between 2 prefix words, hello and OK. O is a magic phone with low false recognition rate and high security. So, our next finding is that we should choose secure phones. For the last factor, order, we randomly changed the order of phone A and phone B and found out that order has almost no effect on security. We also analyzed the combination effect in order to rank the 4 factors. We find that richness is more important than element, than length, than order. By fitting the experimental data, we modeled the PROLE score function as shown in the graph. Now that we have found out how to calculate the PROLE score, we can use the PROLE score to select wake-up words. Are the current wake-up words secure? We assess 30 wake-up words from commercial products using the PROLE score. Here are some results and findings. Almost all commercial wake-up words have enough richness. Some commercial wake-up words have inadequate length. We suggest repeating the words to improve security. For example, Alexa has a length of 6 and a PROLE score of 8.16, whereas Alexa has a length of 12 and a PROLE score of 9.15. Another interesting finding is that Chinese wake-up words prefer repeating, such as 小度小度. This might be designed because of linguistic habits, but by coincidence, this repetition improves security. Another interesting finding is that most wake-up words in English use a prefix such as hey, okay, or hello. Do those prefix words have an impact on Voiceprint security? We compare the average PROLE score of 7 wake-up words with and without the prefix words, and find out that prefix words can improve PROLE score by around 24% because of the increased length, richness, and element, which is the use of secure phones. And the better prefix word is OK. To answer the question in the title of the paper, OK Siri has a PROLE score of 9.4, and Hey Google has a PROLE score of 8.8. So OK Siri generates a more secure Voiceprint. To conclude, we proposed and constructed a scoring metric called PROLE score to evaluate the security of Voiceprint. We explored the correlation between the security of Voiceprint and the speech content. And manufacturers and users can use the findings to select secure wake-up words. In this paper, we investigate the impact of speech contents on the distinctiveness of Voiceprint, with 2,457 speakers and 14,600,000 test samples. We experimentally obtained the correlation between the false recognition rates and the richness, length, elements, and order of phones. We define a PROLE score that can be calculated based on speech content, yet can also reflect the voice distinctiveness. Using the PROLE score, we test 30 wake-up words of 19 commercial voice assistants and provide recommendations for the manufacturers and users. Some possible future work include studying the effect of accent and improving the transferability of metric across models. This is the end of my presentation. Thank you so much for being here, and feel free to leave me a comment to ask any questions. Thank you.